everyone. Today we will see the phase diagram, the solid liquid vapor boundary. Next is the solid liquid boundary. Next one is liquid vapor boundary, and last point is the solid vapor boundary. So, initially we have seen the diagram for these three phases, solid, liquid and vapor together, and the diagram shows all three phases intersects at one point, and that point is called as a triple point of water. So, now we will see one by one each point. So, see, here is the diagram which shows solid, liquid and vapor. Three phases are present at one time, and the plot is of a pressure versus temperature. Pressure is on y axis, temperature is on x axis. So, this is the PT diagram or the phase diagram which is drawn against pressure versus temperature. So, here is the solid, then it will get converted into liquid. So, here is the phase boundary. So, this is the boundary in between the solid and the liquid phase. So, this is the boundary in between solid and liquid. Then next one is a solid vapor. So, here is the solid and here is the vapor. So, this red line shows the boundary condition in between the solid and the vapor, and next one is the liquid and vapor, this one. So, here is the liquid and here is the vapor. So, this blue line is for the boundary condition in between liquid and the vapor. So, we have seen what is meant by triple point, what is meant by critical point. So, this is the diagram which shows all three phases, solid, liquid and vapor are present at equilibrium and they coexist at a certain point. This point is known as a triple point. So, this is, if this diagram is drawn for water, this is the triple point of a water, and at the triple point pressure will be PTP and temperature will be TTP. So, TP represents the triple point and here is the critical temperature. Now, we will see the phase diagrams. It's a plot of pressure versus temperature. The pressure is typically in atmosphere and the temperature is in Celsius or Kelvin, and the labels on the graph represents the stable states of a system in equilibrium, that is solid, liquid and gaseous phases. Then the lines represent the combination of pressure and temperatures at which two phases can exist in equilibrium. So, this dotted line shows there is a combination of pressure and temperature at which two phases can exist in equilibrium. In other words, these lines define phase change points. The red line divides the solid and gas phase. This red line divides the solid and gas phase or the vapor phase. So, this is the boundary in between solid and the vapor, and the red line which divides the solid and gas phase, this represents the sublimation, that is solid is directly get converted into vapor. So, this red line or this boundary shows the sublimation process occurs, means solid is converted into gaseous state, and deposition occurs, that means again gas to solid formation occurs there, and the green line which divides the solid and liquid phases and represents melting and freezing. So, this green line represents solid is get converted into liquid, that is it represents the melting, that is solid is converted into liquid, or if reverse condition is there, it will be freezing point, and that is liquid to solid conversion occurs when there is a freezing. The blue line divides the liquid and gas phases, which represents vaporization. So, here is the blue line which separates liquid phase and the gaseous phase or the vapor phase. So, this blue line divides the liquid and gaseous phase, which represents the vaporization. That means liquid get converted into gas, and when there is a reverse process condensation, gas will be converted into liquid. And there are also two important points on the diagram, the triple point and the critical point. So, these are the 2 points which are very important. So, the triple point represents the combination of pressure and temperature that facilitates all phases of matter at equilibrium. That means solid, liquid and gas, all three phases are present at the equilibrium. And triple point is the point on a phase diagram at which all three states of matter, gas, liquid and solid can coexist. Then the critical point or the critical temperature. At a critical point, we have drawn a dotted line to the x axis, and that will be critical temperature. So, we define critical point. Critical point terminates the liquid and gas phase line and relates to the critical pressure. The pressure is above which a supercritical fluid will be formed. So, at the critical point, the supercritical fluid will be formed. Now, we will see the pressure temperature diagram showing three phases at equilibrium. Again, see here, the pressure is in atmosphere, temperature is in Kelvin on the x axis, and the pressure starts from 0, 1 and so on. And here is the solid present, solid is get converted into liquid. This is the boundary condition between solid and liquid. Then this solid and gas, here is the gas phase. So, solid and gas from 0 to D, this is the boundary condition in between solid and gas. Then liquid and the gases phase are separated by DE line, that is the DE boundary. So, these are the three states of matter, solid, liquid and gas, and they are separated by an imaginary boundary. Then the first one is the solid liquid boundary. So, consider the diagram, here is the temperature and here is the time. So, initially at a higher temperature greater than 0 degree Celsius, the water is in the form of the liquid. When we decrease the temperature, the liquid is cooling down, and due to that it will be converted into liquid plus solid, a mixture. And after decreasing temperature below the 0 degree, the liquid can be converted into the solid. So, that means the solid ice is formed from the water. So, here is the liquid, here is the liquid plus solid, and below the 0 degree Celsius, as time passes it will be get converted into the ice. So, here we have seen in the one lecture the number of phases present. Here only one phase is present, here two phases are present, liquid and solid, and here only solid ice is present. And from this we have found the variable value, and for region A to B, suppose here is the point A and here is the B, C and D. From A to B, variable is 1, from B to C variable f is equal to 0, and from C to D variable value is equal to 1. So, here phases and variables, two things are different. So, liquid is the first phase, then here in middle case liquid plus solid two phases are there, and for third only one ice, that is the solid, is the one phase. So, these are the phases can be represented by P and variables are represented by F, and C is the component. So, this is the phase rule, P plus F is equal to C plus 1, or P is equal to F, P plus F is equal to C plus 1, and here we have taken only one phase, that is why P is equal to 1, F as it is, component is water, that is why it is 1. So, phase will be 1, and when F is equal to 1, that is the variable is equal to 1, that shows only temperature is varied with change in the liquid phase of the system. So, we will see for the transfer of solid to liquid or liquid to solid, freezing or meltings are possible. So, fusion, that is a melting or the freezing curve, this curve is known as the freezing curve or the melting curve. The curve on a phase diagram which represents the transition between liquid and solid state is called as a fusion or freezing curve. So, these two processes are different, melting and freezing. So, as we are going to decrease temperature, obviously freezing occurs, and when we increase temperature, the melting will occur. So, the melting occurs when a substance goes from a solid to a liquid state, and freezing occurs when liquid to a solid state conversion is there. Now, from region A to B there is a liquid state, solidification starts at point B and it will continue to point C, and CD region represents the solid state. So, see here A to B there is a liquid state, then from B to C at point B liquefaction solidification start, it continues to till C, and below the C point C to D there is a complete ice is formed. Now, normally the solid or liquid phase line slopes positively to the right. However, for other substances, notably water, the line slopes to the left as the diagram for water shows. So, you can see the diagrams for water and diagrams for carbon dioxide. So, the line slopes of this phase diagrams are to the right side for carbon dioxide and to the left side for the water, and this indicates that the liquid phase is more dense than the solid phase. And now we will see the next point, liquid vapor boundary. So, this figure shows the rho density is on the y axis, that is gram per centimeter cube, and on the x axis there is a temperature in degrees Celsius. So, this figure shows two different phases, one is the liquid and another one is the gaseous phase. So, density will go on increasing from 0 to 1 and temperature will increase from 0 to 300 and so on. So, the density of the liquid and gaseous phase of water are shown as a function of temperature in this diagram, and at the critical point the densities of the liquid and the gases are equal. So, this rho C represents the critical point at which the density of the water and density of water liquid and water vapors are equal. So, we will see the liquid is more denser than the gaseous phase because here density is increasing, but at equilibrium or at a critical point the densities are equal. And this is the diagram liquid vapor boundary showing diagram. Here on the y-axis there is a pressure, on the x-axis mole fraction. So, here on the y-axis pressure, same here. So, you can take the binary mixture A and B. So, A substance contains Pa star pressure, that is the standard pressure, and B substance have the Pb star pressure, and here is the mole fraction of the A substance. So, when we will draw the plot of pressure versus mole fraction of the substance A, the plot will be like this. Here is the liquid phase and here is the vapor phase. So, these two phases will be separate, and this figure shows the variation of the total vapor pressure of a binary mixture with the mole fraction of A when the Raoult's law is obeyed. So, when there is a binary mixture and the substance A is obeying the Raoult's law, at that time this plot is like this: liquid and vapor, these two phases are separable. So, we will see this diagram in a new way. Here is the vapor pressure and here is the mole fraction. So, this diagram shows, here is the middle part. So, by drawing diagram instead of like this, here this circular part in which both phases are present, liquid plus vapor here, but outside this, at upper side only liquid is present, at lower side only vapor is present. So, by such a way you can draw the diagram of a vapor pressure versus mole fraction, or a diagram which shows liquid vapor boundary. So, this is the boundary condition in between liquid and vapor. Here also this one is the boundary in between liquid and vapor. Now, same way you can draw the diagram, instead of vapor pressure you can write the temperature. So, this temperature versus mole fraction diagram is as like this. Here on the y-axis temperature is there, on the x-axis mole fraction is there, and the diagram is like this. This circular portion which shows, in this portion only vapor plus liquid mixture is there, and outside this here pure vapors are there and here liquid is there when the pressure is constant, and in first diagram temperature is constant. So, only one variable is changing, another variables are constant. So, this circular part shows the mixture of two phases, and outside this vapor and the liquid are separately present. So, this is the boundary. Now, the critical point, the point on a phase diagram at which the substance is indistinguishable between liquid and gaseous state. So, we have seen the liquid vapor boundary. Obviously, for liquid boundaries, the point on a phase diagram, as we have seen the point, critical point at which the substance is indistinguishable between liquid and gaseous state. That means here this is the mixture, vapor plus liquid. So, we cannot identify in between this region separately the vapors and the liquid, because this is the mixture. And vaporization, or you can say this is the condensation curve also. So, the curve on a phase diagram which represents the transition between the gaseous and liquid states. So, when liquid is converted into vapor, the curve is called as vaporization curve, and when liquid is converted, when liquid get converted into vapor, this is the vaporization, and when vapor is converted into again liquid, this is the condensation curve. Now, we will see our next point, the solid vapor boundary. So, as initially we have seen in the first diagram, here here is the solid phase and here is the gaseous phase, and this red line shows the boundary condition in between the solid and vapor phase or the gaseous phase, and the process is known as the sublimation process. So, simply I have written here the same. See here, here is the temperature and here is the pressure. So, QP represents the quasi-static pressure. So, see, initially we have the solid, then solid plus gaseous mixture is there, and then finally pure gas is there. So, as we have seen the cooling curve of the liquid water and the vapor, same way here is the liquid and solid, we have seen the cooling curve, same way here is the curve of solid and the gas. So, initially only solid is present. As the time goes on or as we are going to increase the pressure, the solid plus gas mixture is there, and finally only pure gas is there. So, this is called as the enthalpy of sublimation in between this, and the temperature is called as a melting temperature. So, this figure represents the temperature versus heat curve, and that as the temperature goes on increasing linearly with increasing the pressure in a single phase regions and remains constant along the two phase curves as the relative amounts of the two phases in equilibrium change. So, here are the two phases, solid and the gas. So, initially only solid phase is there, but here in between this solid plus gas two phases are there, and finally only gaseous phase is there. So, this is the curve for sublimation process, and this is a curve of temperature versus heat. So, Q is the heat and P is the suffix, sorry. So, heat at the constant pressure, QP represent the heat at the constant pressure, and on the y-axis there is the temperature. Now, sublimation occurs when the substance is directly get converted into the gaseous state, or the solid substance get converted into the gaseous state, and deposition occurs when the substance goes from a gas state to a solid state. Again solid will be formed, and it is the reverse process of sublimation. Melting occurs only when a substance goes from a solid to a liquid state, and here fusion is when a substance goes from a liquid to a solid state. So, here is the summarization of all the processes as a melting, fusion and vaporization. So, initially first one is the sublimation. In sublimation, solid is get converted into the gaseous state. The deposition is the reverse process of the sublimation. Then next process is the melting process, in which solid get converted into liquid, and in fusion again this is the reverse of melting. Then vaporization or evaporation, in which liquid it get converted into gaseous state, and condensation process is a reverse of the vaporization process. Then the critical point, the point in temperature and pressure on a phase diagram where the liquid and gaseous phases of the substance merge in a single phase, and we cannot separate these two phases. Then the triple point, obviously at this point all three phases are coexist in equilibrium. So, this is the phase diagrams and phase boundaries.